Hi, my name is Bia Stella, and this is ML-D-16, and our project is contrastive knowledge distillation for banana leaf disease diagnosis using sparse capsule networks. For the background and the introduction, bananas are vital crops for food security and economic stability in most tropical regions, and that includes Uganda. But they also have challenges of being affected by severe diseases like the Xanthomonas wilt and Segatoka. Well, the challenge is that farmers face limited access to affordable diagnosis tools, resulting in delayed diagnosis or economic losses. And then the techno solution is that AI-based systems, especially the multimodal learning, offers scalable solutions for timely disease diagnosis and management strategies. For the introduction, here, plant diseases significantly impact yields and farmer livelihoods, yet existing diagnosis solutions are resource intensive and inaccessible to rural farmers. Well, this project integrates advanced machine learning techniques, including the disease diagnosis, using image-based detection, and then providing care tips through a GPT-powered model. For the related works, the CNN-based models like the VGG16 mobile net models have shown high accuracy in crop disease detection, and then the multimodal systems combining visual and the textual data offer actionable insight for farmers. And the relevance of our work leveraging advanced architecture. Our system builds on transfer learning with CNNs and VIT for effective feature extraction. And then we have the multimodal integration, combines the visual diagnosis with GPT-based care recommendations. And the problem statement, well, farmers often lack access to timely, accurate disease diagnosis tools, and then reliance on manual inspection. This leads to delay and inaccuracies. Then there's limited resources in rural settings, and this hinders the adoption of advanced diagnosis systems. Then some of the computational problems is that variability in disease symptoms, complicates the model training. And then the limited labeled dataset constrain performance. Multimodal integration requires seamless communication between the vision models and the GPT. Research questions and some of the objectives is that how effective can CNN-based models like the MobileNet V2 and Inception V3 classify banana diseases from the image data? Then what impact does data augmentation and preprocessing have on improving the model performance? Then the other question is that how can multimodal integration, that is image and text, enhance the usability and accuracy of a plant disease management system? Objectives is to develop a machine learning system for detecting banana diseases using the CNN-based models, just like I'd mentioned, MobileNet V2 and Inception V3, plus other models. And then to include multimodal learning for combining image diagnosis with textual care recommendations to enhance model performance through preprocessing techniques like the data augmentation and normalization. Research contributions, we developed a machine learning system leveraging the CNN-based architecture. We also integrated multimodal learning by combining the image-based diagnosis with GPT-powered text generation for actionable care recommendations. And this is how the methodology looks like. Well, the system, to access the models, there's a user interface where the user has to log in and either upload or take a picture of the image they want to detect for the diseases. And then it's preprocessed. The MobileNet model preprocesses and extracts the features and then makes its prediction. Then after the prediction is made, the API generates the care recommendations for the farmer. That's all I had.
Hi everyone, this is Nyakana Patricia, and I'm going to be continuing from where my colleague stopped. So here we are going to go into the dataset description as well as exploratory data analysis. So our dataset was got from, this is the link to our dataset, it was got from langley.com. And this dataset is designed for recognition and analysis of banana leaf diseases, specifically focusing on three major conditions: a healthy banana plant, a plant that has segatoka, and one that has banana xanthomonas wilt. So this is how our data set is structured. It has images that are in the healthy class and those in the segatoka class, as well as in the xanthomonas class. So during exploratory data analysis, we analyzed some image properties such as the color histogram, aspect ratio distribution, brightness distribution, and this was majorly to identify patterns. That we could use to train the model parameters. Then we also analyzed the class distribution, which showed us that the data set was imbalanced, in that there were more images in the xanthomonas class than in the healthy and segatoka class. Then the corner detection, edge detection, grayscale intensity distribution, those were majorly to capture the special features that our model will be focusing on to make a prediction. So these are some of the images that show the analysis of the data in the data set. We have the color histogram for all the classes. Then we also have the brightness distribution as well as class distribution and the corner detection as well as other image properties. So for our model output results, these are the models that we were able to train. And the best performing one, the one that performed better on the test data, was the MobileNet V2. It shows an 85.18% accuracy on the validation set, but on the test set, it shows a higher accuracy than that. So we decided to go with it. And also the reason that we used MobileNet was that it classified most of the images correctly in their different classes. Moving on, we also did explainable AI techniques to help us determine which features exactly the model was focusing on to make predictions. And we did GradCam and saliency map as well as counterfactual, which just shows us the what if output. What if I put a different input, then what prediction would I get from the model? So for model selection and deployment, the model that was selected, as I mentioned earlier, was MobileNet V2. Because of, first of all, its efficiency and scalability. It's optimized for mobile and edge devices, which our web application will be using as like for users to access the models. Then also it demonstrated high accuracy and robustness in classifying banana leaf diseases during testing. So its performance was relatively good. And then it's also widely validated in image classification tasks worldwide. During model training and evaluation, we deployed the model via render for cloud scalability, and so that it could be directly accessible by farmers on either mobile devices, maybe your phone or a tablet, as well as also a laptop. So for user interaction, the farmer can either upload images through the app, or they can take a picture of a banana leaf image and then receive diagnostics with treatment recommendations in real time. So this is a demonstration of the developed product. Up here, I've put the link to the web application, which provides a user interface where a user can create an account and their diagnosis history will be saved in the database. So this first page here shows the homepage, which has the banana leaf diagnosis, where a user can either upload an image from their gallery or wherever they have their files stored, or they can take a picture. And then when you analyze the leaf, this page gives us the prediction result. And we can see that this leaf was predicted to have Segatoka with a confidence of 89.34%, which is relatively good for the model. And then based on that prediction result, the open AI API we use generates advice based on that prediction. So it gives advice like maybe they can tell you to monitor your plants or maintain proper spacing or remove infected plants that could affect other plants. Yes, so that's how the application works. So some of the IP assets we identified include the domain-specific multimodal training pipeline, where we process visual and contextual data to enhance predictions. Then we also have real-time and edge deployable diagnosis system, which is the web application that we've optimized to work on both mobile devices as well as laptops. So it can work on a phone, it can work on a tablet, can work on a laptop. Then we also have API-based diagnostic inference pipeline, which is the back-end system, which combines the model prediction system, which is the mobile net that provides the prediction, and then the text advice generation, which uses OpenAI API. Then the other IP assets are visualization and performance metrics, as well as scalable and modular system design for farmers. And we also have a farmer-focused user interface, as we can see in this web application. So some of the limitations, the deep learning models that we're training require substantial memory and CPU power to process images and then give a prediction, because most of these models are powered by TensorFlow, and TensorFlow, even just loading TensorFlow, takes a very high amount of memory and CPU power, and some of it we had to pay for. Then we also have the limited data set size, which could affect model generalization and also cause bias by the model, where it just it gives a prediction based on the instance in the class that has more images than the others. Then some of the models that we trained, such as the capsule network and the classic CNN, experienced overfitting, which made it unsuitable for deployment. The capsule network was not properly capturing the spatial images such as the edges of the leaves, the lesions on the leaf, so that made it unsuitable for deployment. Then there are also resource constraints in rural areas because most farmers don't have access to advanced hardware, they don't have access to phones. So this is a limitation where with this application will be hard to use in a rural area. So to conclude, we developed a robust AI-driven system which combines a deep learning model, which is the MobileNet V2, and an open AI API, which uses GPT-3 for banana leaf disease detection and treatment recommendations. Some of our future works, we plan to expand the data set such that we collect more images to improve model generalization and prevent bias by the models, which could cause misclassification. Then we also have model optimization. We hope to optimize the application for low power devices and also extend to rural areas. And then we also have community validation, where we plan to collaborate with local and commercial farmers for real-world testing and refinement. Then we also plan to scale by automating data labeling and using cloud-based systems for scaling. For now, we are using Render, where we have to pay for memory and CPU power. Then lastly, we also plan to combine the system with IoT sensors for real-time diagnosis of the banana leaf diseases. Yes. Thank you.